Newton's cradle may look like a simple toy, 5 balls hovering in the air, held up by 5 strings. What secrets could this possibly be holding? But the more you play with it, the more questions arise. Why does only the last ball move when 1 ball is lifted? Why do 2 balls move when 2 are struck? You may think this is simple. An equal amount moves from the other side for the amount of balls you strike with. But what happens if you take 2 balls from the opposite sides and drop them at the same time? What about when you drop 2 from each side? Why does the middle one never move? In reality, the simplicity of this toy is a mere illusion. An illusion that, when lifted, reveals a surprising number of secrets. In a closed system, the total momentum remains constant. It's neither created nor destroyed, or rather transferred between objects within the system. This phenomenon is called the conservation of momentum, which becomes obvious throughout Newton's cradle. When you give a certain amount of momentum to the first ball, it gets seamlessly transferred to the next. When the momentum leads to the final 5th ball, it cannot be transferred to another ball, so it moves, and the others remain stationary. This is, of course, a simplified explanation. In reality, the momentum is transferred through the stationary middle balls almost instantaneously. This happens because the collisions are elastic, meaning that both momentum and energy are conserved. But what about when you lift 2 balls from both sides? How does the middle ball stay completely stationary? Well, it is governed by the exact same principles as before: conservation of momentum and conservation of energy. When 2 balls from each side collide, their momentum is transferred through the center ball to the opposite pair. Each set of 2 balls takes on the momentum of the other, causing them to move outward while the center ball remains stationary due to the symmetry of the system. While answering these questions, it has become apparent that the conservation of momentum and energy are the 2 bases of this phenomenon. According to the law of conservation of momentum, in a closed system, the final momentum equals the initial. Pi is the initial momentum, and Pf is the final momentum. This can further be simplified into the momentum of the 2 bodies interacting. The initial momentum of object 1 plus the initial momentum of object 2 is equal to the final momentum of object 1 plus the final momentum of object 2. Moreover, since momentum is mass into velocity, the formula can be rewritten as m1 into u1 plus m2 into u2 equals m1 into v1 plus m2 into v2, where m is the mass, u is the initial velocity, and v is the final velocity. But wait, we are forgetting something. Just as momentum is conserved in the system, energy is also conserved. The law of energy conservation states that energy cannot be created or destroyed, but rather transferred or transformed from one form to another. In the case of Newton's cradle, when 1 ball is lifted, it is given potential energy. When the ball is released, that potential energy is converted into kinetic energy. As the energy travels through the system, it is transferred from one ball to the next during each elastic collision. Since the collisions are nearly perfect, no energy is lost to heat or deformation, and the total amount of energy remains constant throughout the system. This is why after a collision, the last ball swings with the same energy as the first ball initially had, but in the opposite direction. But this explanation begs a question. If all the energy and momentum is conserved, why do the balls eventually stop? Shouldn't it go infinitely? Well, the explanation given above is entirely theoretical, and applies only to a closed system. However, reality is far from a closed system. Factors such as air resistance, friction, and sound all affect the duration for which the movement occurs. This directly ties into the second law of thermodynamics, which states that in any system, entropy or disorder tends to increase. But that is another video entirely. So for now, we'll end here. Just remember, in the world of physics, even the simplest of toys can reveal the profound elegance of the laws that govern our universe.